welcome everyone. Welcome to my session, Too Fast, Too Furious. Hopefully it's obvious we'll be talking about SQL Server, speed, concurrency, and correctness. So this is with the context of query execution in mind. If you feel you're in the wrong session from that, then grab a coffee and go to one of the other brilliant sessions that's on. Worth saying that this session's only 20 minutes, so we're probably going to hold off on questions. But if you ask the questions anyway, we'll try and get them from SQL Bits at the end of the session, and I'll try and do a blog post. If we've got time at the end, obviously, I will try and answer them then, but I doubt we will. So I think that's everything I need to cover. Let's get going. And I just need to do, sorry, bear with me a second, and I need to click this button and we are off. The only thing I need to point out on this slide is the evaluation link. I am very happy for you all to lie and say the session was brilliant, even if you thought it was awful. There's also a QR code at the end of this session, which will give you links to all my contact details, this evaluation link, and also links to the source code that you'll be seeing demoed in this session. So make sure you have your camera ready at the end. Alternatively, just email me and I'll give you all those things. That's fine. So probably worth me actually defining what I think speed, concurrency, and correctness is. So for me, speed is all about that motor car, which is speeding down the racetrack on its own in isolation. There's no distractions around it, no other cars, and the track is lovely and smooth and it's plain sailing. And we can think about this in the context of a query running on its own on a server without anything else affecting it. Okay, so that's really what I define speed as. It's how quickly a query running in isolation can run and execute and complete on its own from start to finish. Now, extending this further, this is where we get concurrency, because we will take these single queries running in isolation and then run them all together. And we start getting contention as well between across these queries. Queries start battling for resources and things start to slow down. So a concurrent system is one that can obviously run many, many queries, which moves us on to correctness. And you can really think about correctness as being an expected behavior. So we may get slightly different outcomes leading up to our final behavior. So it may be that our league positions of our constructors here will differ from week to week, depending on how our queries run at the time, but we expect a predefined outcome by the end of it, repeatable behaviors. Now, obviously in a SQL Server context, we have isolation levels which define what outcomes we expect. So we may expect dirty reads, and we will therefore have an isolation level of reading uncommitted. So it's really about expected behaviors. This is what correctness is. Now, at the end of all this, all of these three things kind of work hand in hand together. But what we really want at the end of it is a champion. We want a server which is really performant. We have our winner here in Mr. Schumacher. So I tend to follow some predefined rules in how I go about trying to performance troubleshoot SQL Server and queries in general. And the first one that I want to point out is Occam's razor, which states that entities should not be multiplied beyond necessity. What does this really mean? Obviously, it means that the simplest explanation is usually the best one. So the keep it simple, stupid rule. So my server is running slow. Some idiot has run a really expensive query is probably what the answer is to that. But you know the general approach. Something's gone wrong on the server. Someone's done something. The next principle that I like to follow is the Heisenberg uncertainty principle, which states that the more precisely the position of some particle is determined, the less precisely its momentum can be known, and vice versa. I'll have to take a breath from that. And that really means that the more closely we look at a system in motion, the less we actually see. So what I'm really trying to get at with this rule is that we have to take a very high level look at our server and then start focusing down. Don't jump straight to that query that has very high numbers against it, because it may be the wrong one and you may waste loads of time doing that. Look very high level and kind of get an idea of what's going on the server before you start making these assumptions. The next principle is the Pareto principle, stating 80% of Italy's land was owned by 20% of the population. This is clearly the 80-20 rule. And in terms of SQL Server and performance, we could say that 80% of performance problems are 20% of the queries. What I'm really trying to get to here is that you don't have to solve an awful lot of problems from a performance perspective in SQL Server to have a massive performance boost. And then finally, the last rule I tend to try and keep in mind is Armdahl's law, which is the speed up of a program using multiple processes in parallel computing is limited by the time needed for the sequential fraction of the program. So what this really means is that if you have an execution plan where there is a serial portion to that execution plan, you will never get the performance of that plan running any faster than your serial portion can go. You can't just keep chucking loads and loads of processors at it because it's serial. It can only run on one processor. Okay, so you either have to somehow make that serial part become parallel, or you just bite the bullet and say, right, fine, we're not getting any faster than this. So hopefully that was good for time for me, because we've got a lengthy demo here now. So I will just try and flick over to it. So just to let you all know, this code you can all get out from my repo, as I stated at the beginning of the session. The first file, setup.sql, you will all want to run to set your environment up. It creates a database and puts a bit of data in the database. Okay, so hopefully that has been run and my server is still running, because we could have problems. So we'll jump to the first demo script here, and we're going to talk about speed and concurrency. So I might zoom in a little bit here just so we can make this code slightly bigger. So the first thing I'm going to do is run a very, very simple query. We're going to select from a table, which table one ID here. And is this fast enough? When is a query fast enough? So I don't know about you, but to me that looked pretty darn quick. Okay. Now, if we look at the execution time of this query, in this instance, it was 3 milliseconds. So my senior DBA has asked me, are you happy with this execution time? And I would say, yeah, query is great. But if we just analyze this a little bit, what I'm going to do is I'm just going to say include actual execution plan and run this code again. And we'll look at the stats IO on this. So the first thing that I'm jumping to and starting to scratch my head is I can see that we've got 232 logical page reads. This doesn't sound right when I'm just returning one row. And now if we look at the plan, I'm sure most of you, because you'll be guru level, most of you will probably guess that, yeah, we're doing a table scan here. So the thing I want to point out, hopefully you can see the cost here of this subtree. So the execution plan cost is 0.23. If you can hear meowing, it's my cat going crazy in the background, so apologies for that. So 0.23, what does that mean? Well, obviously the cost is kind of an abstracted cost. It's based upon measurements that Microsoft did in the past, so many years ago. The way that I kind of understand what that cost means is by running the simplest query possible on a server. So maybe you want to do an insert, or maybe you want to do a seek for a single record, and then that cost that you get will probably be the best cost you will ever get on your server. Okay, so that's a good way to kind of compare if a plan is good or not. I can tell you from past experience that 0.02 is roughly the best cost I will get on most servers, certainly this one. So what do we do? Well, I still don't think there's a bigger problem here because that runs pretty quick to me. So what we've got here is we've got a simple update, which is cat's no scratching, apologies. So we've got a simple update, and all we're doing is we're setting a column value to the same column value just because we can. And we're doing this where the ID is based upon a random number that which are generating each time. All right. So we're just doing lots of updates and just re-updating the same information. And what we're going to do here is we're going to run SQL query stress. Now I will try and do a quick zoom on this because I know it's not particularly big. Not sure that zoom worked. Oh, there we go. And I'll just zoom in one more time. Right. So we're going to run 100 iterations over 10 parallel threads, which means we'll do 1,000 updates. And I'll hit go. Let's see how long this takes. Notice we're getting no errors, so the updates are definitely happening. And to me, this looks pretty quick. So we, in 11, 12 seconds, we've done at least half of the workload, and we can guess that this is going to finish in approximately 22 odd seconds. All right, so that's not too bad, is it? Not too bad. And let me zoom back out. So we all know, as I say, you're gurus here, so you'll know we need a clustered index on this table. We're going to specify that predicate that's being used because we want to try and get our seeks working, don't we? So we'll flick back to the test, zoom in again. And this is where I lose my query test. There we go. And let's kick it off, see what we get. And as you can see, this is massively more performance. That's amazing. We've really done a good job here. So let's just analyze what's gone on here. It's not rocket science. We're going to just look at the stats.io again. And if we look here, we see that we've got now 2 logical reads, okay? And we'll look at the execution plan. Oh, surprise, surprise, we've got a seek going on. If we look at the cost, oh, we've actually got better than I thought we have, 0.003 tree cost. Okay, so this is great. All right, so why is this quicker? Well, in isolation, the query running on its own is quick enough, but it's not performant because it's accessing far too many pages to get at the data it wants. All right, it's when we start doing stuff in parallel that things will start interfering with each other and slowing down. So I've got this simple statement which really clarifies if something's fast enough or not. And I state that a query is fast enough if it accesses the minimum amount of pages possible in order to satisfy the result set. Right, so always bear that one in mind. So moving on to the next demo here, we're going to talk now about correctness. This is a particular favorite topic of mine. So we've got some very simple scripts here. And what we're doing, just to describe, is we've got a while loop here, which hopefully you can see. And we are simply looping around this transaction, which initially will delete any records that are in the cast table, and then it will do 10 inserts into that table. So that means that when it loops around to the next execution, when the delete happens, it will lock with an exclusive lock all of those rows. And I will explain why we want to do that in a second. So that's now looping around. And in the next session, we've got something very similar. So we've got a loop again, and we're deleting from a table variable here, just to clear it out so that we can then insert anything from the cast table into this table variable. We're going to see how many rows we got. We would expect 10 because we're either going to be blocked or we'll get 10 records. That's what the transaction isolation should be doing here. Okay, so we're going to run this and see what happens. If we don't get 10, we're going to get a break in the execution. And because I'm actually telling you I'm doing this, you're probably not surprised to see that for some reason it has broken. So what happened here is it did run for one successful execution, but then for the second execution, it only returned 3 records. Now, why is this happening? Well, it's actually an edge case. I've actually written about it in this blog post, but it's really about the way that SQL Server accesses mixed extents. All right, so please read my blog post. I also reference something that Paul Randall wrote about this. Now, is there any solution to this problem? Well, possibly. Let's try running this script using serializable isolation, because serializable fixes everything, doesn't it? Not really. As you see here, we actually introduce another problem. We get deadlocks. That's why we never use serializable. But it did do one successful execution. So this is not a solution really for us, because we'll have to manage the deadlocks and have to replay, and it will be very, very slow. So let's now try a different isolation level. We'll use one of the optimistic isolation levels in read committed snapshot. So we're just going to transition to that as the new default. I will have to connect back here and rerun our loop again. And let's see what happens. Does this resolve the problem? And yes, it does. Of course it does. We'll just check the other optimistic isolation level, which is snapshot, and see whether this resolves a problem. And hopefully we'll get 100 successful executions, which we do, and 10 records. So there are ways around lots of these bad behaviors, and it's best that, you know, you really just need to steer towards the optimistic isolation levels. That's the solution really to those problems. So I'm just going to transition back to read committed isolation. And then we're going to go to the very last demo, which I hope I have time to do. So firstly, just let's make sure there's nothing open. And what we have here is we're going to create a simple table and insert one record in there. And then we're going to start an open-ended transaction. So what we want to do is we're going to update that one record, and we're going to change that value to 1. So because it's an open transaction, that record will now be locked. Hopefully I did that, actually. I don't remember clicking the button, so I'll just double check and then just do that again so we don't get an error. Okay, so we'll switch back into session 2. And so as a developer, I may not want my code to just sit there if we do get blocking. So I may want to set a timeout. And what will happen is my application will detect that timeouts happened and then replay the code against the server at a later stage. So, you know, we're just trying to be efficient here as a developer. So what we have here is a transaction that we're going to fire against the server. We're going to insert one record into that table with a value of 2. We're also going to try and delete a record where the record is 1. Now, because the other session had that record of 1 and is currently an open transaction, we are going to expect a wait or block on that. So let's just run this, see what happens. And surprise, surprise, our lock timeout was honored, and this transaction was, let's say, loosely aborted right now. But let's see what happens. Well, we've got no open transactions. Okay, so if I flick back into this session, and we're going to now commit our record and then do a select from the table and see what's there. Surprisingly and quite worryingly, we actually see that we've got a ghost record in there. Maybe not a good term to use in SQL Server terms. We've got a record that we weren't expecting in there. And what happened is that the lock timeout, this is expected behavior, rather than rolling back the transaction, which you would have expected, its known behavior means that it will allow anything to be updated, inserted, but when the lock timeout happens, it will only roll back the statement where it happens. The commit still happened. So the takeaway from all of this is you as a developer really needs to understand what's going on here. So we've got 1 minute left to wrap up. So what can we do to improve everything? So the first thing that you really need to do, which is probably very obvious, is keep transactions short, reduce complex logic, so we don't have a lot of these concurrent contention issues. Always use optimistic isolation, especially if you're using on disk isolation levels. If you're using optimistic isolation levels like in-memory OLTP, you're very unlikely to see lots of these problems. When you're troubleshooting, always make sure you capture, review, and optimize query plans that are really based upon how often they execute. Because that 10-minute query that runs once a day isn't really going to cause much problem. And then finally, well, not finally, sorry. Next, we want to implement new technologies to improve concurrency, like one that I've already mentioned, maybe column store, maybe even delayed durability. And then finally, always test your results in parallel to prove that that the consistency and performance still continues. That wraps up my session. We are out of time. All linked session feedback can be obtained from this QR code. Thank you very much for joining me today, and enjoy the rest of bits.